Hi Seb.
Hi Seb.
Welcome to our first executive interview here at our R&D center in beautiful Bangkok in Thailand. You gave me a good idea. We might call this a tree-side chat.
Yeah, I love the tree-side chat, yeah.
The reason why I thought we're sitting down today is because we just celebrated a huge milestone. We launched our first use case for our cryoimmunostaining technology.
Yeah, that's big news, yeah.
In Frankfurt, in Germany. And given you're the guy who invented it all and who founded the company, I thought there's no better person to talk about it than you. So maybe just for starters, why is it such a big deal that we're at this point now?
At the top line level, I want to say that obviously changing anything in medical practice is extremely hard, and usually it takes a very long time to change medicine. So that we're able to change how pathologists perform immunostaining, what it's called, how they do their diagnostics is a very big deal, I think.
So you already mentioned pathologists. So could you maybe explain who uses the technology and what exactly they're doing with it?
Yeah, it's really the pathologists, and the pathologists are obviously the only doctors who diagnose cancer. Any cancer diagnosis comes from a pathologist. So if we give them better tools, that's a big deal. Now, pathology is a big field, and they look at any tissue from the body, but also at liquid samples from the body.
And what's the advantage of liquid samples?
Liquid samples are really a very fascinating field because liquid samples you can always get in a minimally invasive manner. If you want a tissue sample, you have to make a cut and cut it out, and that's not always very convenient, right? But a liquid sample, you can take a needle, a very thin needle, a very small needle, and get it out. And nowadays, with CT-guided, ultrasound-guided technologies, you can reach basically any body cavity and suck out liquids.
So how have they analyzed these body liquids before X-ZELL came along?
Well, that's the sad story of the past 40 years in pathology, I want to say, because what they had to do, they had to pretend they're looking at tissue. So they had to actually take these beautiful fresh cells and convert them into little tissue pieces.
Okay.
And that is a very laborious process because you have these cells in liquid, and then you have to artificially clot them. So you create an artificial little block, you clot it, put it in paraffin, slice it, and then put it in your tissue processing routine. And this whole upstream takes 48 hours, more than 48 hours, and is a very, very manual process that cannot be automated. Otherwise, it would have been automated already. So we shorten this to 4 hours and get rid of all this upstream process.
Yeah, so that would be the next question, obviously. What does X-ZELL do about this whole process?
Yeah, so we are able now to deliver a diagnosis in 4 hours, what took before 3 days, and we cut out 90% of the labor. And we do not, and that's very important, we do not require more time of the pathologist. So before you had like 3 days manual labor in the lab, and then the pathologist spent about 2 minutes per case maybe to find out what it is. Now you have 3 hours in the lab, and the pathologist spends 2 minutes to find out what it is. And that was a critical achievement to actually make it usable in routine.
Okay. So there's two parts of it. There's the lab part that we streamline, and where we cut out this old cycle of preparation steps.
Right.
And then there's the pathologist part, where the whole diagnostic work and the evaluation happens.
Correct. That's really the challenge in medicine, right? You always have a lot of people involved in a process. So you have to make sure that everybody wins. You can't just make it better for the lab and then the pathologist needs 1 hour. Then it's dead. It's not going to happen.
So we're talking about pathology, and then we're talking about cytology.
Yeah.
So we have to understand what the difference is. So when they analyze body tissue that was obtained surgically, we're talking about pathology.
It's really tissue pathology.
Okay.
And then cytopathology you could call maybe single cell pathology or liquid pathology. Okay. But both is pathology. So pathology is everything, and then you have the big part, tissue pathology, 80%, and 10 to 20% is cytopathology or cytology.
So the summary is they're responsible for all the cancer diagnoses in the world. If they work with minimally invasive samples, you may refer to them as a cytologist. So that's kind of a subcategory, the way I picture it. But they effectively don't have the technology to do a good job.
Well, they've been doing their job with the existing technology, but the existing technology is not ideal. And I think you could say I'm biased, I want to push out our technology, but the best proof is that in cytology, with the existing technology, in 50% of cases, you don't get to a diagnosis because it doesn't work. And why does it not work? Because you lose when you clot your cells, when you convert your cells into little tissue blocks and put them in paraffin and slice them, you lose a lot of information. You lose a lot of cells, you lose a lot of information, and you need quite a lot of cells to come to a diagnosis. So we get rid of this whole upstream process and put everything on one single laboratory slide. So we don't lose information. And that will clearly, we already see that happening, that will clearly improve what we call the diagnostic yield. So the percentage of successful diagnosis will go up. What we have to keep in mind and be aware of that pathology is still largely qualitative. That means you look at tissue patterns, you look at cells, at single cells. Are these cells normal or not normal? That's the basic question you ask yourself as a pathologist. Am I looking at an atypical cell or a normal cell? If it's an atypical cell, it can be cancer. There's some other diseases that can interfere with this diagnosis, which makes it tricky sometimes, but it's qualitative. There are some parts that are quantitative, but it's really qualitative. So pathologists work from images, from looking at patterns. It's pattern recognition, basically.
And how do we have to picture it? How did they do it yesterday, and how are they going to do it tomorrow?
So if you look at these very small cells or cell aggregates, to understand what they are, you have to understand them at the single cell level. And what they need to do is, you need to stain them. You stain them to detect different properties called antigens. So the cells express proteins that makes the cell alive, right? The DNA is not alive. The cell only becomes alive when the protein is expressed. That is read from the DNA. So there's proteins, and there are hundreds or thousands of proteins in every cell. And the pattern of these proteins determines what the cell is. It's the identity of the cell. And pathologists know that certain combinations of proteins are characteristic for certain disease, cancers. So they need to detect them. So what they do now is they have, for every antigen, they make one slide and see if that antigen exists on these cells. But the problem is that they have to do make an average of 4 to 5 slides per patient case to come to a conclusion. Sometimes I run out of material before. That's the 50% that don't work. And sometimes it's very difficult to say because you cannot slice one cell into 5 slices. It's too small. You have actually different cells on your 5 slides. And then you have to figure out what you see here and you see there and you see there and you see there. How does it connect on one cell? And that's where a lot of training and a lot of experience come in to take the right decision. Now what we do is we put everything on one slide and stain up to 8 antigens on one cell. So you actually see it like a stack. You see everything on the same cell. So that's why we like to call it single cell diagnostics or single cell cytology, because we can now characterize one cell very well. You only need one cell you only need one cell before you need at least 5 cells, right? For the same information. But you also see it on one cell, so that helps them to really really makes diagnostics easier when you see it.
But then there's one more aspect, and we always talk about the fact that it's digitized, right? So why is that important?
How did the pathologist look at his 5 slides until now, right? In his microscope, in his bright field microscope. So he looks into his microscope. and he has to change the slide when he wants to look at the next slide. So we only have one slide, and what we do is we take, we're using fluorescence technology, fluorescence staining, where you can use all colors of the rainbow to look at different cell properties. So every property of the cell, every antigen is stained with a different color. You acquire this whole image stack with the different colors, and then we show it on the screen. So in one glimpse, you can see the combination of antigens of that particular cell. And once you have done that a little bit, it's very, you can see this in seconds what the combination is. So that makes the pathology a lot faster.
It's a tough sell sometimes, right? There's a lot of vocabulary you have to explain, a lot of concepts, immunostaining, antibodies, different types of samples, pathology, cytology. Is there any way to condense it into an explanation that is more widely understandable without all the technical vocabulary?
We knew that the pathology market is huge. And we knew that the systems are really optimized for tissue pathology because that's the larger market, 70–80%, depending on the lab. So then we realized that these 10–20% of cytopathology were really neglected and had to go along with whatever the tissue pathology market offered. But given the fact that we are moving towards a minimally invasive diagnostic, that's really not a niche anymore. That's a big problem because it could do so much more. In 1969, we landed on the moon, and then for the past 50 years, nothing happened. Why? I don't know why, but it didn't happen. And I look at it in a similar manner. We were on the right way, and we deviated because it was maybe not the mainstream way, but it's really high time to go back now.
It started in 2010 with a cell separation patent. That's where you decided to, I guess, change pathways into the more entrepreneurial lane. Then you, to give it a quick summary, in 2015-16 went to Y Combinator, the biggest accelerator program in the world. Made a top 10 finish there, and that's when I came on board and the kind of current team formed. But our focus was at that time liquid biopsy, so the analysis of small blood samples to predict or diagnose cancer. And that's the biggest question the internet has been asking, I guess, on the back of the recent announcement. How did we get from blood analytics to cytology? Slash the analysis of common body liquids like lung fluid, etc.
Yeah, as it goes, sometimes it's good to have a very high goal to stretch yourself quite far, because if you want to analyze atypical or cancerous cells from blood, I want to say that's probably the most difficult thing you can do in cytology, because those are very few cells and nobody knows them because they're very hard to find. But we wanted to do that, so we had to improve our detection technology and our analytical capabilities to be able to routinely do that. That made our platform so robust. But we didn't think about this cytology application 3–4 years ago, that's true. So how did we come to think about it? Is anecdotal in a way. COVID locked everybody down. So I was sitting here, you were in Germany.
I was in Singapore.
No, you was in Singapore. You were in Singapore, later in Germany, and it was obviously not easy to operate. So I was going through our old data, mining images, and we got to present this, the liquid biopsy from lung cancer. I got to present it at the European Conference of Cytology in Wrocław in 2021 virtually. So it was a 10-minute presentation. And these virtual presentations are no fun, right? You sit in front of your screen, talk into your screen, and then it's over and you don't know what happened, you don't see anybody. That was actually nice, the nicest then so far, because the panel asked some questions in this virtual environment. So the panel said, we as cyto what did they say? We as cytomorphologists love your images. So they were pathologists, but they said also pathologists are cytomorphologists. Never mind. They loved it and asked some questions. And a few weeks later, we by email we got the abstract award of the conference, which was really a total surprise because I presented it as a startup, as a commercial entity, a startup from Bangkok, into my screen, and then we get the academic abstract award. So that really woke me up in a way. So I called you and said, hey guys, these cytologists, we never thought about them, and they really like the images. We have to find some more cytologists. Yeah, and then we found Dr. Butman. He said, like, if you can do this for my routine cytology, not talking liquid biopsy, for my routine cytology, where I also look at single cells, that could really help to change the way I do diagnostics. And then it all came together because our platform was made for very, very few cells. So while the cytologists think they have few cells, for us it's a lot of cells, right? Because we come from a different application made for very few cells. They think not enough cells for their cytoblock is few cells, but that's a lot of cells for us. So we were able to really streamline this whole process and make it very practical for routine diagnostics.
So we aimed really high and built a whole platform of technologies to analyze blood.
Yeah.
Knowing that it's kind of a blue ocean scenario because analyzing blood is
it's a holy grail, as some people.
It's the holy grail in that space. And then by fluke over COVID realized that part of the platform that we developed for that, we can apply it to everyday lab work right now.
And much easier for us. And reimbursable, of course.
And that's a big thing, right?
Yeah, it's routine diagnostics, so labs get paid for that. And they have the freedom of choice of technology as long as the related technology. So the old technology stains antigens, these property of cells. We stain antigens, property of cells. So you can use the same reimbursement codes. And every country has a reimbursement code for that kind of staining. But I want to say that the liquid biopsy is of course not out of the picture because in the end, blood is also obviously it's also liquid with cells. If you think in where's the liquid in the body? It sits in body cavity. So you have the cavity of the lung, you have the cavity of the pleural space, that's the space between the lung and the rib cage. You have the abdominal cavity. So all these cavities can have cells or cell suspensions you can get to with a needle. But the biggest cavity is actually the blood circulation, right? And the only challenge with this blood circulation, if you want to find cancer cells, is that there are many healthy cells. So you have a lot of healthy noise you need to look through to find the cancer cells. But in the end, it's also cytology.
So we've hit this huge milestone and we know what's around the corner. But what's really interesting, obviously, for everyone is also what's the next big thing. Where do we see this go in the mid and long term?
AI will come in and play a bigger and bigger role in everywhere in our lives, also in medicine. But it's of course a delicate balance because right now you wouldn't want to have AI sign off on your diagnosis, right? So when do we reach that point? Because that's a real inflection point. When you get a diagnosis by AI, that's different from anything that happened before. Obviously, AI can take a supportive role to make the work to help pathologists become faster, to save labor because we don't have enough pathologists. So I'm not talking about replacing pathologists, but I'm saying that the majority of the world's population doesn't have access to good pathologists. That is the problem we need to solve. We don't want to replace pathologists, but we need to leverage the few we have to help more people, right? So how is that possible? And then this is where AI can come in strong, probably quite soon. I think a lot about that, and we are very aware of that. We've started to use AI to pre-screen, say, what we see. And the capabilities it's very clear, they're amazing. They're beautiful. So we are ready to roll when it's time.
So there's a strong pipeline as well, right?
Yeah. We have an AI annotation team in house. We know how to annotate well. We know the ins and outs of annotation, which people don't talk about, but it's actually a big issue to talk about. We're already rolling, but we're rolling under the radar. But there's of course the regulatory implications. Who's paying for that? There's no AI reimbursement, right? Who's paying for that? So you have to keep all these things in mind. But we're definitely ready to play that card when it comes to it.